Okay, well, good morning, everybody. As Temi said, I'm Peter Messmer, and I'm located in Zurich. I'm working for NVIDIA's so-called DevTech team. So this is the organization that helps people like you to make maximum, or to take maximum benefit of the available GPUs. Parts of our job is to teach classes. The way this is currently set up is that it's a beginner's class, but I mean, it's your time. So please let me know if you're completely bored, if you think that we should go at a slower pace, if you want to have some clarifications, just interrupt. The program at the moment, and again, that's just tentative, that's kind of the overall outline of what we're planning to do, but before lunch today, we will just get a first CUDA program written, compiled, run it on 30, and I'll tell you a bit about what CUDA is and how you need to think about the different parts. Again, you've heard a lot about OpenACC over the past 1.5 days. So then getting on to 30 and compiling a code there should probably not be so difficult. But yeah, let's see how far we get in these 1.5 hours. Then in the afternoon, I'll talk a bit about Kepler and CUDA 5.5. I hope that at that point we have sufficient context to kind of appreciate what these changes mean. And then after that, there's going to be a first part of a 2-part session on optimization. GPUs are there to accelerate, so optimization has to be a part of any kind of CUDA class. And yeah, there's going to be breaks. After that, we will have also a session on tools after the optimization part. That might be a bit confusing, so I'll probably need to do a few forward references in the optimization part, just for the profiler and some of the debugging stuff. But yeah, bear with me. It's not rocket science. It's just how to use a tool. And then afterwards, we will actually go and dive into hand tuning a piece of code this afternoon. All right. GPU architecture overview and CUDA programming. Oops, this sounds a bit loud, but okay. So when talking about GPUs, it's also worthwhile to look back a bit and see how did we get there, right? GPUs still have a day job, and that's the entertainment industry. So GPUs are made for graphics. It started out somewhere in the early 90s with the fixed pipeline. Oops, sorry. With the fixed function GPUs. So those were devices that had specific silicon for specific functions, for specific operations like shading a triangle and so on, that was available on those early GPUs. And then at one point, people realized that there's much more flexibility if you add programmability to these devices. And eventually, but at that point, there was still the vertex shaders and the pixel shaders, so basically pieces of program that operated on 2D data structures and pieces of program that operated on 3D data structures. And it was not until 2008 when then people realized that you can use the same programming infrastructure, the same silicon for doing both the 2D operations and the 3D operations. And that's basically when CUDA was born. So CUDA was kind of, it says 2006. I mean, until it was actually available, it was more like 2007, 2008, until people got their hands on it. And since then, all the newer generation GPUs are CUDA capable and will stay CUDA capable in the future. Just the size of the bullets, by the way, is proportional to the amount of transistors that you have on these devices, and it's yeah, those are massive, massive devices. Now, with the introduction of the programmability, people started to play around with GPUs for doing scientific computing, and at the beginning, it was actually using still these devices that had the split between the pixel and the vertex shaders. But then with the advent of CUDA, there was just much more activity on the in academia for doing GPU computing. And nowadays, I mean, that's why you're here. It's pretty much mainstream in the scientific computing world that you at least want to understand how GPUs work and how you can take advantage of them. So the system, as you have it in 30, is still a combination of both a CPU and a GPU, where the CPU is optimized for minimal latency. So you want to be able to quickly switch between different operations. And the GPU is optimized for throughput. So you want to be able to push as many operations through the device as possible. And just to give you an illustration here, right? In order to get to the very low latency that you want to get on this on the CPU, there is a lot of infrastructure on the chip, like large caches to make sure that you have massive amounts of data readily available. There is a lot of control flow silicon, out of order execution stuff, and only a few parts that are actually dedicated to the compute. On the GPU, the balance has shifted, right? We're saying you need tons of arithmetic and logic units. The L2 cache can shrink because we're saying it doesn't really matter how long it takes to get data from the DRAM. That can take quite some time, as long as we have sufficient work to hide that latency. And that's going to be one of the major parts of the optimization session this afternoon. It's all about this latency hiding, right? You want to make sure that you have sufficient work in your application to hide all these latencies that are introduced when you're fetching data from global memory or when you're processing a complex operation. And there's no claim here that one is better than the other. It's just you're covering different parts of the application with these different types of processors. And just to give you a picture here of what it means with the latency optimized processor. Right, so on the CPU, you have what? Nowadays, something like 12, 16 cores, somewhere around there, 8. And so you want to switch between different tasks on each one of these cores. So you want to make sure that when one task is running, every memory access, which is shown here in white, every memory access is as short as possible, and you just fetch the data and you continue processing. And then every once in a while you have a context switch, and you move on. On the GPU, we're saying it can take quite a bit of time until data actually arrives. So you have a piece of work that starts, and now it has to wait for a certain period of time until data arrives, and then it can continue. But luckily, we have sufficient work to hide this entire latency. So from the outside, it looks like the GPU is busy crunching away on numbers all the time. So what does a GPU consist of? Again, one of the problems also with CUDA is that we have a lot of new terminology, and in some cases it's a slightly confusing terminology because there's terms that are used also in the CPU world that clash. So yeah, we will talk quite a bit about the terminology, but when we talk about the GPU, we usually mean the GPU board. And the GPU board, so if you have a PC at home, it would be the thing that you stick into your PCI Express slot. And that one contains, in addition to some logic for talking to the bus and so on, it basically contains global memory and the actual processor, the streaming multiprocessors. So global memory, that's currently limited to something like 6 gigabytes. Actually, we just announced a new device that has 12 gigabytes of memory, a K40. But for the devices installed here in 30 and in Daint, it's going to be 6 gigabytes. The bandwidth is relatively high. These 180 gigabytes per second. You will see a lot of different numbers. The 180 gigabytes per second is a good number to keep in mind for rough estimates. This is with error correction turned on, and it's achievable with a fairly simple piece of code. The fact that we can do error correction basically sets apart the devices that are produced for mainstream, for gaming purposes. Those are the ones that cannot protect errors or cannot protect their memory hierarchy for errors, as opposed to the Tesla and Quadro products, so the high-end products that have the capability of actually detecting and correcting errors that happen anywhere in the memory hierarchy. And then attached onto this global memory, we have the streaming multiprocessors. So these are the actual processors, and I'm coming to that in a second. Now, the way you're doing the heterogeneous computing, and that's what you've looked at with OpenACC for the past day. Basically, you're starting out on the CPU, and you have the PCI Express bus that has to be crossed in order to move data from the CPU to the GPU. And then you're instructing, again, from the CPU, the GPU to process something on this data. And then finally, you get the results back to your host system. Now, the way it's being described here is actually kind of the quote-unquote classic CUDA way of looking at things. So where you really have the GPU as an attached coprocessor. Now, there has been a lot of technologies, especially introduced with CUDA 5.5, that kind of start to disrupt this picture. One of the changes is that you can do now directly MPI from the GPU memory to a remote node without having to manually load things into host memory and then do MPI from host memory to the remote memory. So that's one technology that's now available that can actually, you still need to initiate it from the CPU side, but you can give to MPI just a pointer that points to data on the device and say MPI send, and we'll grab it and move it to the remote GPU. That's one of the changes. The other changes is that the GPUs themselves can now create work for themselves. So it's no longer that every time you want to get the GPU to do something, you have to involve the CPU. The GPU can now make decisions by itself and create its own work. This is known as CUDA dynamic parallelism, and we will talk about this afternoon. Now, coming back to the actual GK110 chip. So again, here it's getting a bit hairy. So GK110 is the processor chip that sits on the GPU. What you have in 30 is a so-called K20X GPU. A K20X, so that's the overall board with the memory. The K20X GPU has a GK110 chip on it. However, the architecture of the chip would allow to have up to 15 streaming multiprocessors that are sitting on a single die. The devices that you have in 30 have only 14 of those enabled. And when you buy a K20 GPU for your workstation, most likely it will be a device that only has 13 of the SMXs activated. So that's kind of the different SKUs that we have for the different products. It all hinges on the question of how many of the streaming multiprocessors are enabled. And based on that, you will see a different, for instance, different numbers of CUDA cores. You will see a different peak memory bandwidth, and so on. So the architecture itself allows up to 15 SMXs, and the K40 actually has all 15 turned on. But the devices that you now have installed in 30 and in Daint are coming only with 14. Other good cornerstone numbers that's sometimes useful just for back-of-the-envelope calculations is you can reach about 1.2 teraflops on one of the K20s. Again, it's just, even if you're just saying I can get 1 teraflop with one of these devices, that's good for these type of back-of-the-envelope calculations when you want to figure out how much speed up could you achieve with a certain optimization or by going to GPUs. Then the other number that's somewhat relevant are these 2048 threads that you have on each one of the SMXs. So let's go back again. Here, you're seeing the 15 SMX that sit on a single chip. And now we're zooming into one of those boxes, into one of these streaming multiprocessors. Each one of those can have up to 2,000 threads that it keeps track of at any given time. This doesn't mean that all these 2,000 threads are in actual processing stage. It's just that they're in whatever part of the execution pipeline. And the other technical data is basically just there for reference. Well, one thing that's somewhat interesting is, the throughput of floating point, double precision floating point is obviously lower than single precision floating point. I mean, the devices are still designed for single precision arithmetic. They're very good at double precision performance, or performing double precision operations, but you're paying a penalty. So the double precision throughput is whatever that is, about 2.5 or so lower than the single precision. Or is it 3? It's actually a full 3. Yes? No, those are for 32-bit integers. So any kind of, so all the operations at the very end are starting out as 32-bit operations. So when you're doing a 64-bit integer operation, you're basically pairing two 32-bit operations. So
can I expect the same speed down that I have for floating points?
No, so the factor there for integer 64 is going to be a factor of 2, because you will have to. And now there's right. So for instance, if you do a 64-bit add, it will be broken down into two 32-bit adds with a carry bit, carry forward. There is a certain chance that you're introducing an additional dependency, because you can only start the second operation once you have the first 32 bits added, because you need the carry bit. If the device is completely full, then this shouldn't pose a problem. It can be an issue when you're, that happens quite often when you need to do integer, when you need to do address calculations. And so it can become an issue when you have not sufficient work to hide the latency that you're introducing by the full integer operation pipeline. Yes. Okay. So those are the cornerstone numbers of the for the instruction pipelines, and then we have some additional goodies on each one of the streaming multiprocessors. First of all, they have a huge amount of registers. All these registers are 32-bit. So again, when you want to do double precision floating point arithmetic, it actually uses 2 registers for each double number. And the other thing is the so-called shared memory. That's a scratchpad, very fast memory that you have access to from within your kernels, and allows you to do cooperation between individual threads. Okay, so now how to program these devices. Basically, yesterday you looked into OpenACC as a mechanism to quickly take a code that was written most likely for another architecture and move it onto GPUs. This is only one of the 3 approaches that we recommend. The lowest hanging fruit is just to use libraries. And I'll talk a bit about GPU accelerated libraries this afternoon as well. That can be very beneficial just to quickly get something on the device and not having to worry about the actual parallelization aspects. But what we want to focus on here is CUDA, so using programming languages to explicitly program the parallel devices. I'll talk about the libraries this afternoon. Okay, what is CUDA? When you were one of the persons who started to monitor CUDA back in the early days, at that point, CUDA was just an extension to C. But over the past iterations over the past releases of CUDA, it actually has morphed into a full C++ based language. Now, CUDA is really just C++ plus a few extensions. So there's a few syntactic elements and a few semantic additions. The goal is to give you a mechanism of expressing this massive amount of parallelism that we have on these devices. And you don't want to have to worry about the nitty-gritty details of like how you want to schedule the operations and so on. It wants to allow to easily express this parallelism. And so we will come to this expression in a second. And what CUDA defines, and again, that's one of those places where we have a name clash. It both defines a programming model, but it also, in particular, it defines a memory model that's very close to the underlying architecture. So let's talk about the programming model. Similar to OpenACC, your CUDA application consists of is very centralized around the host code. So you're starting out with a serial code on the host, and then every once in a while, you're kicking off these pieces of parallel code. We call those a kernel. And these kernels execute on the GPU. Again, the GPU we often just refer as the device. And so you have these flow that sits on the CPU, and then every once in a while kicks off work on the GPU. You're asynchronously continuing to work while the GPU works on the CPU, and then you can query your data and get the data back from the GPU side. Now, these kernels execute a huge number of threads. So a kernel is basically the instruction flow, the sequence of instructions of a single thread. And the model allows you to write a kernel that is being executed just by one single thread on the GPU. It works, but it will be fairly inefficient. Remember the slide that I had at the very beginning where we said that, well, it takes a long time until the GPU processor gets the data when it requests one from memory. Well, if you just have a single thread that executes, then you're exposed to this whole duration, this whole latency of asking for memory until you actually get it. And the GPU doesn't do anything in that time. So what you want is having sufficient work to hide all these latencies that you introduce. So you want to have a massive number of threads that execute these kernels. Now, switching between threads comes at no cost. There is no cost associated with having an instruction from one thread being executed, and in the next instruction having it from a completely different thread. The hardware keeps track of all the different threads in what stage that they are, and can therefore switch and find out what is the next available thread that could be scheduled to execute and to not let the device idle. Just once more, the terminology. So on the CPU or on the host, we talk about function execution or calling functions. On the GPU or the device, we talk about kernels and launching kernels. Launching is basically the act of kicking the GPU off to do the work. So I think we've covered most of that. Here, just kind of the way you can think about it is that you have all these different threads, so whatever that is, 7 threads here. And the way you would write a particular function is that you're looking at just the control flow of a single thread. And there's mechanisms to identify yourself. In this particular case, the thread ID. This tells me I'm thread number 5. And so you're fetching from the input array the 5th element because you're thread number 5. You perform a function on it, and then you're writing it out again. This is a fairly typical minimal kernel that you would see here. Now, I heard that there was already some discussion about the thread hierarchy during the OpenACC talks. So this is just repetition, but it's kind of a very fundamental concept. And so I'll spend a little bit more time on it. Basically, assume that you have, you've written your kernel and you have sufficient parallelism to to work on the GPU. So you have, whatnot, 100,000 threads. Okay? Now, these threads are grouped into thread blocks. And each one of those thread blocks can contain whatever, let's say 128 threads. Actually, the maximum number is somewhere in the 2000s. And then, so the threads are grouped into blocks, and all the blocks together form a so-called grid. So when you're executing a kernel, you're actually executing a grid of blocks of threads. It's not no rocket science or anything like that. It's just terminology. What is introduced here is yet another term that will become important this afternoon during the optimization part, but is not really necessary to think about in the first iteration of your programming, which are the so-called warps. Even though the GPU makes it look to you as if you had 100,000 independent threads of execution, they're actually not executed as 100,000 independent threads on the device. The device executes threads in groups of 32, or in so-called warps. So you have 32 threads that are grouped together. And at one point during the optimization process, thinking about the warp granularity becomes important. But for the first design, or at the very beginning, it's really, you can simply ignore the fact that you have yet another level of granularity that is present in the architecture. Now, why do we have this hierarchy of the threads and the blocks and the grids? Well, first of all, there's hardware equivalence to them. So basically, a thread is what is being executed on a single CUDA core. So this is the smallest instance that you have on the device. A thread block is being executed on one of those 14 streaming multiprocessors that we had in the pictures before. So you're guaranteed that a thread block can execute on these on one streaming multiprocessor. And if you remember, we also mentioned that there is this shared memory. Right? Now, given that a thread block executes on one SM, well, they can use this shared memory to exchange information. So the key distinguishing part of a thread block is that it can actually cooperate with threads. Threads within the same thread block can cooperate. The different thread blocks that you have in a grid, they can be dispatched in an arbitrary order onto all the different streaming multiprocessors that you have on the device. As we will see in the next slide, this also gives us the scalability. But this tells you that there is no simple way of communicating between the threads of thread block number 1 and the threads of thread block number 2, because there is no defined order. There is not even a simple way of synchronizing the two thread blocks. And so you shouldn't design your algorithm in a way that would require communication between the thread blocks. So we had this one that this allows the threads in the same thread block, right? They can actually share the work, they can communicate, and they can synchronize. Now, as I said, there's the fact that we have the thread blocks that are that can be executed in an arbitrary order gives us automatically some scalability. Imagine the following grid where we want to execute these 8 blocks. Well, you could be running on a simple device that only has 2 streaming multiprocessors. What would happen is that the first 2 blocks get dispatched onto the 2 SMs that are available. They process, and then the next 2 thread blocks get dispatched, and so on and so forth. Now, without changing the code, by moving this to a device that has 4 SMs, well, it will automatically be able to take advantage of all the 4 streaming multiprocessors, but now only take half as much time to complete. And you can scale it up as high as you want. So the fact that the model doesn't make you any guarantees about the relative execution order of different thread blocks gives you a scalability that you would have a hard time to otherwise implement in a reasonable fashion. However, it puts the burden onto the programmer, which is, sorry, but makes our life a bit easier. And that's frankly the most challenging part about GPU programming or any kind of massive parallel programming, because which is this separation of or this design of your algorithm in a way that expresses this hierarchy of parallelism. So you shouldn't think about global reductions across all the threads. You can do it, but it's much easier when you can say, I'm aware that I have these individual blocks that can communicate with each other, and they execute in an arbitrary order. And yeah, so by the way, yeah, that is not related to CUDA, or that's not related to GPUs. That also on any other massively parallel device, you will be facing this challenge. I mean, that's the intellectual challenge of designing a code for a GPU, which is how can you express your algorithm in this in such a hierarchical way. Okay, now somehow you need to be able to make decisions based on where in this whole flood of threads you are, in this whole grid. And so both the threads as well as the blocks have mechanisms of getting a unique ID. If you're familiar with MPI, it's a similar concept to MPI rank and MPI size, MPI com rank and MPI com size. Basically, you have an ID that gives you the thread ID within a given block, and you have an ID that identifies your block within the grid. And those IDs can be 1 or 2 or 3 dimensional, but and they're kind of defined at kernel launch time. Here are the names. So thread IDX is the thread index, and block IDX is the block index. So that gives you the unique ID of your particular thread. And then in order to make your code a bit more generic, it's useful to be able to query what is the number of threads within a block. For that, you have the block dim variable, and the grid dim tells you how many blocks you have in your overall grid. So when you're now launching a kernel, the way you're doing this is by having this slightly modified C function syntax. And so this is where CUDA actually appears in your code, right? It's this triple bracket notation. There's a few keywords in addition, but that's the key addition to C is this triple bracket notation. And what that does is basically it says this kernel should be executed in a grid of a given dimension, and each block, so a grid of so and so many thread blocks, and each thread block should have so and so many threads. So basically with this launch, you're saying, I want to create y number of threads, and now go and do it. And just down here as an example, it's somewhat a bad example because we're using the same number of both for the grid and the block, so it's not very illustrative. But basically here you're creating a 2-dimensional grid. dim3 is just a type, a predefined type that is a 3-dimensional struct that is initialized as, in this case, only with 2 dimensions. So the third dimension is 1. And so 16 by 16 thread blocks, and each thread block contains 16 by 16 threads. So we are launching, yeah, somebody can do the math, a large number of threads. Yeah.
Excuse me?
Yes?
The example below this, 500.
Right. So this one means, so 32, so we have constructors for this grid, or for this dim3 that take 1, 2, or 3 arguments. So if you're just creating the grid with a single argument, it basically sets, so it sets the x dimension, but the y and the z dimension are set to 1. So with 32, with just providing a scalar, you're basically creating a grid that is 32 by 1 by 1 thread blocks. And each thread block contains 512 times 1 times 1 threads. So here we are launching 32 times 512, 16K threads. So how do the kernels actually look like in code? Probably the smallest kernel you can do. Actually, there is one that's even smaller that is a no-op kernel. But the smallest one that does something is the following here. As you can see, it's really just a C function with the added keyword underscore underscore global. Now, what does global mean? Global means that it's a symbol that's both visible from the CPU side as well as on the GPU, right? Because eventually this symbol has to live on the GPU. The code for this piece lives on the GPU. However, you need to call it or to launch the kernel from the CPU side. So that's why both the CPU and the GPU need to know about the name of this kernel. And here we have, we're passing in a parameter, DA. That's just convention or can be convenient to label variables that live on the GPU with a D for device. Use whatever terminology or whatever convention makes most sense to you, but we oftentimes use D to label device variables. So this kernel takes an array on the device, and it sets the elements to 13. Okay. Now, as you can see here, we don't have any dependency on the thread ID or. So if we're launching now a grid of, let's say, 10,000 threads, and we're launching this kernel, this minimal kernel, what will happen? What will happen is that all threads will take this pointer on the device to this vector, and every single thread will write 13 to element 0. Right? Just to the location of this, the target of this pointer. Pretty dumb, but it works. I mean, it's nothing wrong. It's just not particularly spectacular. So this is a way of creating a huge race between all the different threads that all write into exactly the same location. Most likely, that's not what you wanted to do. Most likely, you want to have something like the one below, where we're doing an assignment. Again, we have the global keyword here, and what the kernel does is that we compute an index of our vector, and we assign the value that is also being passed in to this particular index in this array. And the index, we have now this ugly-looking expression, which, again, is a very common pattern. Basically, with this here, you're computing the linear index of your thread in this vector. Because if you're ignoring the first part here, it's just depending on your thread ID. Right? So each thread has his own thread ID, and it will write into the location of the vector at your thread ID the value that is being given. Now, this would limit you to the maximum number of threads that you have within one block. And so if you want to have a larger vector with multiple blocks, well, then you will end up with having to do a calculation like the following, where you're taking your block ID, and you're multiplying it by the number of threads that you have within this block. This one here? No, well, the block dimension is the number of threads within a block. There is no thread dim. So let's go back. Here. Look, you have the thread index within a block, and the block dimension is so big. and you have the block index in the grid dimension. Yeah, yeah, it's a bit. Yeah, again, it's just convention. Okay, and so as I said, this is a very common pattern. You will see this almost in every kernel in one form or the other. Yes?
The way I read this is the first thing, for instance, is that I allocated memory on my host, and I passed the pointer to my.
That's a very good question here. We haven't talked about allocating data on the GPU or on the CPU. Here, we're just assuming that we're passing in a device pointer, right? And that would mean that's a pointer that points to data that is located on the GPU, right? So it's possible to dereference DA from the GPU. At the moment, this means it has to be a pointer that actually, it has to point to a location on the GPU. That's one of the big changes for CUDA 6 that we will talk about tomorrow, is that we're introducing now unified memory that will allow the GPU to grab data straight from the CPU side without any explicit transfers. But let's leave that to tomorrow. Right now, this would mean that you have to have allocated data on the GPU, and now all these threads are writing into this allocated chunk on the GPU at the first location, at the 0 element. And the same is true for this one down here, right? So we're assuming that we're passing in a so-called device pointer, so a pointer that points to data on the device. I'm not sure how useful that is. It's just one thing, and maybe some picture. I'm a very visual person, and so I like pictures, but might be just more confusing. I am not going through all the details, but again, when you get the slides, it can be useful to work out the math. Basically, what we're doing here is we have a vector of 16 elements, and we break it into blocks of 4 threads each. And it just shows you like what are the different predefined parameters in each one of these blocks. Right, and to come back to your question, or to the question before about the whether it should be thread dim, as you can see here, the block dim for each one of those will be. The light just went on. Did I press a button somewhere? The block dimension of each one of those will be the same. It's always 4. And the grid dimension we're not even referring to here. The grid dimension would be, again, as well 4, because we have 4 blocks in the grid. And as it was mentioned down here, right, this is just for illustration purposes. In a real code, you always want to make sure that the number of threads in a block is at least 32. Because I mentioned that before, we have this granularity of 32 threads that form a warp. I'm sorry for all the words, but so you have the 32 threads that form a warp, and you always want to have multiple warps, or one or more multiple warps per block. Here's just to show how this looks like in the comparison between a pure CPU code and a GPU code. Right? Because eventually you're probably facing the situation where you're taking your code and you want to move it to a GPU. So you're starting out with this on the left-hand side. Right? You have your main, or whatever it's called, your outer function on the CPU, and you're calling a function increment CPU that should just increment all the elements of A with the value B for n elements in a vector. And the way you're writing this is in C is you have a float star, so a pointer to an array, and you're subscripting your A with an index, and at each location you're adding B to the value. So that's a fairly straightforward loop that you're performing on the CPU. Now, what you would do in CUDA is basically just getting rid of this outer loop. right? You're blocking out this loop because you're saying these operations can all be done concurrently. There's no dependency between individual iterations. So you can just launch a single thread for each one of these operations. And that's exactly what we do here. The main meat of this kernel is just A of index equals A of index plus B. Now we have to be a little bit careful. First of all, we need to find out what is index. And so instead of having the loop that gives us the value for index, we just have to go through this calculation of our thread index based on the thread ID and the block ID and the block dimension. And then there is one thing that people oftentimes forget, namely, you're launching multiple blocks, right? Your grid consists of a certain number of entire thread blocks. Now, if the number of elements is not a multiple of your thread blocks, well, you might end up in a situation where you have no work for all the threads that you have within the same thread block. So for instance, if my thread block is 32 elements wide, and I want to perform this operation on 33 elements, well, I need to launch 2 thread blocks. But one of those thread blocks will contain just a single thread. So we have to safeguard this and make sure that we're not accessing data out of bounds. In many cases, the GPU is fairly unforgiving and creates something equivalent to a segfault, so you will notice that fairly quickly. We have just to do some advertisement for this afternoon, we have a tool called CUDA memcheck that is fairly powerful to detect situations like this where you're accessing out of bounds memory. Okay, so this is the body of the kernel where we're just describing what one thread would do. And now instead of having the loop in this function, we're moving this into the driving application here in the main program. So we're launching the kernel, but now on a grid that has, well, we're first deciding what is our thread block size, and then we decide how many blocks that we need, which is just the number of elements divided by this thread block size. And yeah, as you can see, we need to take the ceiling of this ratio, and this can lead to the situation where we have more threads than we have elements in our array. So with this, you basically know how to write kernels. Just for illustration, you can do the same thing in 2D. So with 2-dimensional thread blocks. Now there's always a question like, how do you decide whether you want to have a 1D grid or 1D thread blocks and so on? The idea is to add additional flexibility. So if your algorithm is really suitable for 2D indexing, if you're working on images, for instance, well, 2D thread blocks might make sense. Or if you do dense linear algebra, 2D thread blocks can certainly make sense. If you're just working on vanilla vectors, 1D vectors, there's hardly any reason to go 2D. There is actually a reason for going into two-dimensional grids, simply because there is a limit to the dimension of a thread of a one dimension of a grid. So you can have a maximum of 65K blocks. So if your vector is very, very large, and you will need more than 65,000 times whatever, 1,000 threads that you have within a thread block. So if you need more than 65 million elements, at that point you run out of indices, and you will have to use a two-dimensional indexing case. But yeah, that's for later on. That's when you really are facing a large, when you're operating on very large problems. Okay, so far we talked about the kernels, how we launch them, the syntactic elements that we need to introduce in order to express the fact that we're now performing operations on the GPU. Now we will talk a bit about the different memory spaces. So the memory model that we have is again very hierarchical. we have the host memory. That's the one that you access from your CPU. And then you have the so-called global memory. That's the memory chips that sit on the GPU board. So this one is accessible by all the threads, and whatever is written into global memory stays there for the duration of your application, or until you deallocate your memory. And then within the streaming multiprocessor, you have shared memory. That's the memory that it can be used to exchange data between threads. And then you have the registers. So that's data that's private to each one of the threads. And it's actually, you can perform operations on it, so that's very fast memory. Now, registers, even though we have a huge number of those, it's a limited resource. And so when your kernel requires more data, more state than can be fit into registers, there's also so-called local memory. So that's memory and memory space that's for each, that is set aside for each one of the threads. But it's actually being placed in global memory. So while registers are very fast, shared memory is very fast, local memory is as slow as global memory. So you will be hit by the latency for fetching data from global memory when your kernel uses too much state to keep everything in registers. So that's another one of those optimizations that we will be facing later on is you want to make sure that you're using as little local memory as possible. You want to be able to keep almost everything in registers or in shared memory. And just again, in pictures, the whole thing, right? So each thread has access to its thread local or its thread personal registers. It has access to the local memory, and all the threads together can exchange data through shared memory. And then the kernels can access, or the entire grid can access global memory. And so if you want to exchange data between multiple kernels, the only way to do that, or between multiple kernel launches, the only way to do that is to write data back into global memory and then read it back from global memory. And then ultimately, at the last level of the hierarchy, you have data exchanges between the GPU and the host. Those are the ones that go through the PCI Express bus, and so they are relatively expensive, actually very expensive. Just to give you a feeling, I mean, bandwidth here between device and GPU, we're probably talking about 5 to 10 gigabytes a second. For this here, between global memory and the streaming multiprocessors, we're talking about, let's say, 200 gigabytes a second. And then up here, we're talking about terabytes a second. So just for to give a feeling of what orders of magnitude difference that we're talking here. Okay, so that's the memory hierarchy. Now, so we covered kernels. We know now where the data can live. It can be on the host, it can be on the GPU, it can be within the streaming multiprocessors. Now, how do we fit this all together? So, as you ask, the question is like, where is my pointer pointing to? How do I get my data on the GPU? So, what a CUDA application usually needs to do is to start out with GPU memory management. So you need to allocate your memory spaces on the GPU. You need to transfer data from the host to the GPU. Remember those pictures with the arrows I showed at the beginning? And finally get the results back. And in between, you then need to launch the kernels that perform the actual operations. By the way, for all of this, there is the so-called CUDA C programming guide. All of the documentation of CUDA is available at docs.nvidia.com. So that's a very useful resource. The guide is, unfortunately, in the meantime, fairly thick. So you have to set aside a little bit of time to read through it. But what really matters are just the first few chapters. So you're still down to about 10 pages or so that you actually need to read. So how to allocate memory. So now we're looking into the memory management. Again, it's the host that allocates memory on the GPU. So it's a regular C API or a host-side API. And as in C, you have malloc, free as the basic functions. And so what you do is you have a CUDA malloc instead of malloc. And you're specifying the number of bytes that you want to allocate. And then you have to have a pointer to a pointer. Well, you want to write into this pointer the pointer that you finally want to. Now I'm running out of pointers. The pointer that to the pointer that sits on the host side that points to data on the device. So that's slightly different from a regular C malloc, right? The C malloc actually returns the pointer that you just. It returns the pointer to the chunk of memory that you just allocated. Now, we decided not to follow that approach because we wanted to be able to return error codes for all of the CUDA API functions. And so we said that's more important than being equivalent to the somewhat hacky form that C does it with returning the pointer. Because if you want to check for an error in a malloc, it's somewhat a hairy business. So here, if it was a true CUDA application, you actually would check the return value of CUDA malloc and make sure that you've gotten the memory allocated that you wanted. But the price that we pay for that is that we cannot just return the pointer, and so you have to put in a pointer to the pointer in the call. Long story short, yeah, just follow this pattern. Free, the same. There, you don't just need to provide the pointer and freeze the block on the GPU. And for mem setting, so this is, with this operation, again, that's executing on the CPU. You're giving it a pointer that points to data on the GPU, and you're setting n bytes, in this case, to the value 0. So here you can think of, you're launching a kernel on the GPU that sets all the elements that are pointed to by DA to 0. Okay, so now we can create data on the GPU. The other thing we also need to do is to get data from the host to the GPU and the other way around. For that, we have memcopy functions. Not spectacular. You have the destination pointer and the source pointer, and then you have an enum that gives you the direction. So depending on the context, especially depending on the enum, one of those two guys is most likely a device pointer, and one of them is a host pointer. So you can do memcopy host to device. This means that destination is device. So this is a pointer that was allocated with CUDA malloc. And the source pointer is on the host. So this one was allocated with a regular malloc. There's the reverse of that operation, device to host, so to get data back. But there's also device to device and host to host copies. That's basically just for symmetry purposes, that you can also use this operation to just move data on the device from one block to the other. What is useful to know or to keep in mind is that these memory transfer operations are all blocking. I think I mentioned at the beginning that kernel launches themselves are non-blocking, and you actually want to maintain a lot of asynchronicity between the GPU and the host, right? Because otherwise, while the GPU is working, you're just blocking the CPU from doing anything reasonable. But a good application will actually take advantage of both of these resources. Would be a shame to just leave your, 8-core CPU idling. So what you want to do is you just want to kick off the GPU work and continue work on the CPU. However, this can get you into tricky situations about figuring out in what state is my GPU now and in what state is my CPU. And so the only point where they join or where they need to talk to each other is during memory transfers. And so that's why mem copies by default are blocking. And so then at least you're on safe grounds again, and you know that in what state that the two devices are relative to each other. There is non-blocking forms of the memory transfers. So if you really want to get good performance, you might need to look into that. Okay, I talked enough, so it's up to you. Write the program, and I think that's actually very helpful. So I don't have any pre-made example for this one. So just write a program that creates an array on the CPU, transfers it to the GPU, and gets the result back to the CPU. So we're not launching a kernel at the moment. We're just transferring data from host to GPU all the way back and print it out. I'm giving a few hints here. One is how to compile. We haven't talked about the tool chain so far, but we have a special compiler driver called NVICC. And what you want to do is you give it your sample1 file to compile. You can also ignore the output name. And what is somewhat important is that you specify the architecture. So you will want to use the --arch equals SM35. And then the two functions that you need are CUDA malloc and CUDA memcopy. I'd say go. Yes?
For the execution, remember it's a trace, so AP run, not MPI run.
Oh, see, yeah. So by the way, yeah. I mean, it's a serial code anyway. Yeah. So sorry for the yeah. It's not MPI run there. Yeah. Right. Let me fix that one. Sorry. So if they don't specify anything, they won't get one automatically. Yeah. Yeah. So let's get rid of this one. So this one you should automatically just get the single node. And in a few minutes, I'll just put up the the solution. I'm usually not patient enough to give people enough time, so I'm just putting this one up. Sorry, well, you feel free to not look at the screen. What? You want me to remove it again? And by the way, the hands-on this afternoon, for that we will have predefined samples. So it's not supposed to be a typing exercise. But again, I think it's very helpful to, for once, sit down and really think about what is my minimal program that I need to do to execute something on the GPU, to transfer my data there and get it back. And yes, I'll just, again, don't look at them at the screen if you. NVICC should not complain If you're using NVCC, it includes them automatically. But yeah, you can definitely add the CUDA.h if you. So just maybe to go a little bit through these bits and pieces that we have here. Right, we have our main program, and we have a vector on the CPU, actually two vectors, right? Vector in and vector out. That's simply to make sure that we see whether we've done anything right or not. And we just initialize the input vector. So the first thing we do is we allocate data on the GPU. And again, this is not meant to be production quality or anything like that. It's just as an example. So we have 10 elements in our vectors. So we malloc 10 integers on the device. Right? And so this here is now the address of this integer pointer. So this is the pointer to the pointer on the device. And then we memcopy from the vector in that we have initialized onto the device vector. And we say we do a memcopy host to device. And again, it's n times the size of int. And as the next step, we then get the data back. It's exactly the same thing now, device to host instead. And we have to flip the order of the device pointer and the host pointer. And then we're just printing out whatever, one of the elements. Because we're nice, we're also freeing memory at the end, and that's it. Yes?
You just have a device array. It's called
No. No. Yes. Yes, and we actually did up here, right? Right. But yeah. But otherwise, yeah, you would have to malloc it on the host as well. Yeah. Say it again. If.
You didn't initialize it on the host.
Yeah.
Right.
Exactly. Yeah. Yeah, it's completely separate address spaces, right? And so if it's not allocated on the host side, you get a seg fault. Actually, I hope I have a connection here. Nope. Sorry, let me put this up again. I'll try it later to get a connection, but I still hear frantic typing, so I assume that not everybody has finished yet. Has anyone had success in compiling and running it? You want to load either, the simplest is probably CUDA toolkit. So module load CUDA toolkit. So for you, or for those who already have completed, the next exercise is to write a kernel that takes this data there and changes the sign for all the integers that are larger than 5.
N equals 50, for example, and I launch only 32 threads.
Yeah.
The vector, only 32 values of the vector will be updated, the rest won't be touched.
Right, correct. Yeah, but you still will transfer. So that's an interesting question. So if you now had a kernel, right, that would be, well, or let's put it this way: if n is 10, but let's assume that we're only moving 5 elements. So here, for the mem copy, we would only use 5 elements. Instead of n, we would just move 5. It would only touch those 5 elements. And now if we would launch a kernel on that data, well, and we would use more than 5 threads. Those, we would have a bunch of we would only launch 5 threads, sorry. If only using 5 threads, then everything would work as expected because we have 5 elements initialized. We're working on 5 elements, and then we're getting 5 elements back. Perfect. But if we would be running with 10 threads now, well, 5 of them would be working on uninitialized data. Or, I mean, you could transfer 10 elements and then only work with 5 threads in your kernel. Well, the top 5 elements would simply not be touched. They would just come back as they were shipped there. Yes? Yes. Oh, sorry, yeah.
Would you mind explaining this
Right.
architecture?
Yeah, so the architecture thing. I'll have another slide about the compile trajectory this afternoon, but basically, we have the situation that we have to assume that people use GPUs that are fairly outdated for a certain period of time. Right? And we want to keep the flexibility of adding new instructions as we go. Right? It's not that back in 2007 we defined an instruction set and we leave it at that. We want to be able to augment it with stuff that comes along. And so you want to be able, you want to specify the generation of architecture that you're working with at compile time. By default, NVCC compiles for generation 1.1. So that's a old GPU architecture. Now this stuff will still run on the modern GPUs. So you still will be able to, yeah, you can, even without the ARC SM35 flag, you will be able to run that code. However, there's certain features that you won't be able to have access to with the 1.1 architecture. In particular, printf from kernels will not work. And that's kind of the debugging tool number 1 that we will get to. And so it's, given that all the devices on 30 are SM35, are the 3.5 generation, yeah, just throw that flag in there to tell the compiler that you're generating code that will run on the 3.5 architecture. Okay?
And I know you said it already, but what kind of modules do I need to know?
It should be CUDA toolkit. So it should be module load CUDA toolkit. But let's see if I can make this a bit bigger. Maybe at one point I even get a connection here. Oh, let's see. Nope. Yeah, I'll over lunch I'll debug my connection. All right, so I just want to cover 2 more things before lunch. So I'll skip ahead and go to the other examples. Right. What we've done with the first example is just move data between host and GPU. And now the next thing, as I said before, is will be to add a kernel. And right, we've looked so far into the qualifier __ global __. So that's when you declare a function as global, it's visible to CPU and GPU. Now there's a few more. In theory, you can label every single function with __ host, just to indicate that this function should be visible on the CPU and can be executed on the CPU. There's the equivalent, which is device. So if you have a kernel and you want to modularize it somehow, you can break it up into individual device functions. These device functions will not be callable from the CPU, because a function that has the label device is not visible on the CPU, but it can help you just from a software engineering point of view. And then finally, you can also specify a function as both. Can I speak? You can specify a function as both host and device. So you can say this function will be visible to host and device, which is equivalent to global. Or in many cases, it's for functions that you kind of helper functions that you want to use within a kernel. Then you specify them as device and host, because you can use them both just from the device or also from the host side. I just talked about those parts. We discussed the kernel launch parameter or the launch configuration quite extensively before. And so here I'm just putting up the result of this exercise when you're saying you want to flip the sign of the elements in your vector. So I have a lot of dots here just to say this is exactly the same as you've written before for the first example. But if we want to add a kernel now that flips the sign, so here we have the guts of that kernel. I just called it kernel, and it takes a pointer, and this is now a device pointer. And as you can see, I've already violated my own convention. So it's a slightly better visible if you're labeling it. I just imagine a few weeks from now you're going to look at the code. Well, if you clearly mark them as D or whatever, vec _ D, then it's fairly obvious that these variables actually live on device memory rather than on the host side. So I'm taking a pointer to this device vector, and my thread ID at the moment is just, or my index is just a thread ID. So I'm limiting myself to a fairly small number of elements that I can work with. And I'm safeguarding against, it could be that I'm having too many threads, more than I have elements in my array. And for each one of the valid elements, I'm actually setting the vector to either the value or either the value or the negative of the value, depending on what the value is. Yeah.
Can this thread ID be negative?
Nope. Thread IDs are unsigned. Yeah. But it's oftentimes helpful to keep them as signed integers. First of all, the thread ID is limited between 0 and 2048. So you're for a single block. So there is no chance that you would overflow. And the compiler can do some additional optimizations when it's a signed integer as opposed to unsigned integers. There is some. Yes. And yeah, so in theory, it would even be sufficient to have a short int. Okay, so this is the kernel itself. And then down here, you see the launch configuration. As I said, we're just using the thread index for our index, so we are limited to a single block. So we're launching a kernel. Well, our grid contains just a single block and 100 threads in per block. Now this is obviously a complete overkill because our vector length is only 10 elements. Right? So that's why we're also passing in the number of elements. In our case, n is 10. So we have a grid with 100 threads, but only 10 of them will do actual work. All the other threads will just fall through this particular conditional here because the thread ID for those will be larger than 10. So we passed in n as 10, and my thread ID will be larger than 10 for most of the threads. So what we've done so far is now we've moved data from host to the GPU. We launch a kernel that is embarrassingly parallel because we're not doing any kind of communication between the elements in the kernel. And then we move the data back to the hosts. Ooh, which file? Interesting. Interesting. Can you try it again?
So maybe is it if there are two? I mean, I can Google it, and it's not so bad. Now it's gone.
Can you this minus arc? It's minus minus arc equals or minus arc, right?
No, it's single.
Single and then without the arc. Single minus and then without the equal. Yeah, so in this case it's with the single dash.
Why did it say single dash if it's double dash?
So, try it. No, without. It would be single dash and then without the, yeah, SM35.
Ah, sorry. Hey,
Interesting.
Number changes, so it's
Right. This is a temporary directory that it's
yeah,
trying to
we are
create,
sharing
and
all the same, so that,
oh, you're all sharing the same account?
no.
No.
But it's just TMP. So I don't know how
Mhm.
this is created. This is the
Right. It's a temporary file that is being just created by the.
because it changes all the time, so it cannot be that I'm hitting only bad ones.
Um, sorry, can I just quickly try this one?
You have some module.
Oops.
Oh, sorry, it's called 04.
Um,
I haven't just
now it's you just need to make sure, yeah, that that the other user is not at the same time using the same.
we should synchronize it.
Are you now on one of, did you run a salloc before?
No.
Okay, yeah, try that one.
Yeah, because then it goes to a different node. Then yeah.
Right, so if you're seeing the problem that it complains about the directory that already exists, try to salloc, so get yourself onto onto one of the, get yourself an allocation and then compile there. So when you see, again, I don't have, if you're just SSHing onto 30, again, I don't have it there, but if you would SSH onto 30 and then you just run an NVCC of your sample 1.cu, then you might run into the situation that it complains about a file that exists. So instead, what you want to do is just do in a salloc, get onto one of the, well, get yourself an allocation. You're not actually on the compute node, but get yourself an allocation, and when you then run nvcc sample.cu, then it should work.
Which one?
Well, I'm currently not on even on one of the nodes. Correct. Exactly. So it will always be broken up into warps. So the granularity is always at the width of 32 elements. Now, in your case, with a GPU with 48 cores, yeah, that's a weird generation. So that's a previous generation that had these half warp things. But now on the Kepler size, you actually just have multiples of 32. So that's quite a bit simpler. Exactly. Yeah. No. So nowadays there's no more half warps or anything like that. It's everything is full 32 element wide. Well, it's still allocating warps of 32 threads, but it executes them in halves. Right. Exactly. I mean, that's the picture we had before. Where was that? Bear with me. Right, it's basically what happens here. You can imagine that it's a hypothetical streaming multiprocessor that can execute exactly just 32 threads at any given time, right? So you would have just these 32 threads, but now given that those guys are waiting, it will swap in the next set of 32 threads and work on that. Now this on the same streaming multiprocessor, you will have more than just a single warp that executes. And that goes exactly in that direction, that you want to make sure that you have lots and lots of work available, right? So on a current generation streaming multiprocessor, it can track up to 64 threads at any given time. So you could have 64 threads that are being in one state of execution at any given time. And yeah, you don't really need to have all these 64 threads available, but you can go up to that. If you would have more work than that, then the scheduler on the GPU itself will not dispatch these blocks to the streaming multiprocessor. But so just as a rule of thumb, I'm coming to you in a second. Oh, no, currently they're not. But I can give them over the full lunchtime. We can PDF them and put them on somewhere available. Okay. Yes. Memory pages? If you're online, yeah, go to. So no, it doesn't have man pages, but it does NVCC ---- help. Gives you information about the compiler. It gives you a flood of output, so you want to pipe it into something. Right, and for the reference you want to go. And again, I'm not online at the moment, but it's docs.nvidia.com. Oops. Okay. And exactly, and there is a manual for the compiler.
No, I meant just like, for instance, the return value of CUDA malware.
Right, and so there is a reference manual available at docs.nvidia.com as well. So when you go to, can we? I'll do that in the afternoon. I'll show the website, yeah. But it's basically there. You have the whole documentation. And all the return values and all that. Okay, so I think that was pretty much what I wanted to get through. Actually, no, there was one more example. And again, I'll give you the slides afterwards. But the last example that I wanted to do is now on this vector that we've uploaded, and we messed around with some of the elements independently. Just compute the finite differences on it. Right? This is kind of the generic example where you need to communicate with your adjacent, with an adjacent thread. And I just show you the kernel how this looks like. So the way you want to work in this case, is that you allocate shared memory. Okay, we have n elements for our vector length. That was the n that we declared before. So we define now an array of n elements. Again, we identify ourselves, and if we're shorter, if we're a valid thread, so one that has that is within the extent of our vector, then we're loading from this vector an element into shared memory. Okay, so that means thread 0 to 10 will just load data from global memory into shared memory. Then we have a function here called sync threads. This basically just says we have to wait now until all the threads within our thread block has arrived at this point. Because we want to make sure that all the elements of the vector have been loaded into shared memory. And then after that, we can compute our finite differences. Obviously, for the last element in your vector, you don't want to touch an element that's outside of the vector. So that's why we're now limiting ourselves not for thread ID less than n, as in case of loading, but as less than n minus 1. The last element will not compute a finite difference. And then each thread just fetches, oh, and here I have a typo, sorry. Each thread fetches its own element from shared memory, and it fetches the one element above. okay? And then finally, once it has computed this finite difference, it writes it back into the vector in global memory. Yes? This lowercase n here? This one there? Haha, no. So let's go back. So here it's a bit. Let's go back to this one here where we see all of it. Right, the capital N is a preprocessor N, and to share that this guy is passed in as a parameter. The size of the shared memory when we allocate it as we did down here. If we allocate a vector this way, it has to be known at compile time, and so it cannot be passed in as an argument. There is ways of dynamically sizing your chunks of shared memory, but for this example, I didn't want to do that there. But yeah, no, good observation. Yeah, so this actually has to be an uppercase N. But only everybody in the same thread block, right? So again, remember you have your grid that contains a whole bunch of thread blocks. But sync thread only says those threads within one thread block need to wait for each other. There is no global synchronization. So there is no way, no light way mechanism to synchronize between multiple thread blocks. Yes?
This kernel only works if you have just one.
Correct. Well, it will also work when you have more than one block, but it will produce garbage. Yeah. Because the second thread block, again, if you're assuming that you have multiple thread blocks, well, one thread block will see the original value of vec. The next thread block, depending on when it's being executed, will already see the modified version of vec, right? We're storing the finite differences back into this vector. So, yeah, it will have a non-deterministic behavior, because depending on in which order that these will be executed, you will end up in different results. Yes, purely demonstration purpose example, limited to a single thread block per grid. Okay, this is all I had for the morning, and I leave